talk and kind of stall, and hopefully at the end of my long ramble that we're having right now, eventually the audio will come in, and then you'll be able to hear me, and then we'll be all set to go. Today we are talking about lens equations. Now, you know that we started out by talking about mirror ray diagrams, then we talked about mirror equations, then we talked about lens ray diagrams, and now we're talking about lens equations to complete our little, what do you call this, a series with 4 parts? I don't know, but that's our situation that we have going on here. We're going to talk today about lens equations. Now, these 2 equations that I have written here, these are equations that you should recognize as the mirror equations. Ooh, whoa, I'm going way too fast for my little computer to be able to handle such things. You got it, guys. The mirror equations. And now, you're going to see that the mirror equations, we got this one, which is officially called the mirror equation, and then this one, which is called the magnification equation. What you're about to see is that the mirror equations are actually very similar to our lens equations, and I'll show you how you have to alter these things to turn them into the lens equations. So I'll get out a different colored pen here. Let's go with purple. Actually, I'm changing my mind. I'm going with brown. Okay, let's go ahead and alter these things. Well, first we should probably cross off the word mirror and label them lens. And that's it. Those are all the changes that you need to make. You're saying, wait a second, Miss Wilson, you're telling me that this equation that was our mirror equation is also our lens equation, and this equation that was the magnification equation for mirrors is also the magnification equation for lenses? Yep, sure am. I'm telling you these are the exact same equations for lenses as they are for mirrors. What you're going to see in this lesson is that pretty much everything that we're going to do is a little bit repetitive and a little bit redundant, and pretty much everything that we're going to do you've seen before. But before we can try a practice problem here, we got to take a look at our sign conventions. Let's toggle over to our sign conventions. Here are our mirror equation sign conventions. You wrote these down last time. We said that focal lengths are positive for converging mirrors, negative for diverging mirrors, distances are positive for real images, distances are negative for virtual images, heights are positive for upright images, heights are negative for inverted images, and same thing for magnifications. They're positive for upright images, and magnifications are negative for inverted images. Well, now we got to talk a little bit about our sign conventions for lenses. I've written out the sign conventions for lenses just a little bit lower on this document, so let's scroll down and find them. There they are. Take a look at them. Look real close. If you look closely, you'll notice that, wait a second, Miss Wilson, are these sign conventions exactly the same sign conventions as the sign conventions for mirrors? Yep, absolutely. They are exactly the same sign conventions. We got the same equations and we got the same sign conventions. You're going to see that your work today is going to be very, very easy. Only difference here to point out. We see that converging mirrors give you a nice positive focal length here, but converging mirrors are called concave mirrors because converging describes what they do to light. Concave describes their shape. They're shaped like this. The difference here is focal lengths are still positive for converging lenses, but we call converging lenses convex lenses. That's your only difference here, is that it's both positive. Focal lengths are positive whether you're converging a mirror or whether you're a converging mirror, converging lens, but we call those types of mirrors and types of lenses different things. So pay attention to your vocab there. Other than that, completely the same. Not a single change that we have for our sign conventions. And with that, now you're ready to try a practice problem. Let's go ahead and try it. Open up your textbook to page 501 and take a look at question number 1, and I will do the same. We're going to start here with a little practice problem. This practice problem is coming to you from, let's change our color, shall we? Let's try purple today. This practice problem is coming to you from page 500. 500. You can do it, computer. 501. And this is question number 1 on that page. Here's what it says. It says that you have an object that is placed a distance of 20 centimeters away from a converging lens of focal length 10 centimeters. It asks you to find the image distance and magnification and use 3 adjectives, or it doesn't say use 3 adjectives, it just says describe the image, but we're going to use our 3 adjectives to describe the image. Anytime you do a lens equation problem, you are also going to draw a diagram with it. Same thing with mirror equations. Anytime you do a mirror equation problem, you're also going to draw a mirror ray diagram. The question is not, do I draw a diagram or not? The question is, do I draw a diagram to scale? Or do I draw a rough representative sketch where I still use a ruler and I still follow the 3 rules, but I'm not measuring everything out with my precise measurements and my centimeters on my ruler? For this problem, we are going to practice with a 2-scale diagram today. So first things first, before we can do a 2-scale diagram, we are going to need to write down our knowns and unknowns. I got a number here. It says we got an object that is placed 20 centimeters. You got it, computer. You can do it. Make a 0. 20 centimeters. Away from a converging lens. Hey, if you were to label this number right here, we would label it as the distance to the object. And if you had to give it a sign, we would say that it is positive 20 centimeters. Distance to objects are always positive. Always, always, always. Then we got another number here. It says that the focal length is equal to 10 centimeters. Hey, quick check, are you going to call this focal length positive or negative? You said positive, because it's a what type of mirror? Converging mirror. All converging mirrors have positive focal lengths. And last, we'll write down our unknowns. We are looking here for the distance to the image. Sorry, my computer is so very laggy today. And we're looking for the magnification. Those are our 2 unknowns. I'll treat to the distance to the image like part A and the magnification like part B. Let's go ahead and get started with a diagram. First, take out your handy dandy ruler and draw yourself a nice principal axis here through the center of your page, and I'll draw one on mine. Oh, I do not like that line. Let me try again. Okay, nice principal axis. Get my ruler nice and lined up here. Like that. Okay, I still think my line is too long, so I'm going to try again. And actually, I'm going to go up to this line here. Okay, so sorry, everybody. You're probably way done with your line by now, and you're like, Miss Wilson, can you please take your sweet and precious time? Because, wow, you know how to take a long time to do things. Okay, here we go. Next, can you please draw... Oh, not like that. Okay. I'm going to erase my mirror and lens equations here. I'm going to get them out of the way. Next, can you please draw a dotted line through the center of your principal axis? I'll draw mine in just a moment here. Let me get this cleared out and grab a pen, and we're ready to go. Okay, draw a nice dotted line through the center of your principal axis. I'm going to draw mine right here because that feels good to me. Okay. Okay, kind of excessively long. And then please draw a nice converging mirror. Remember, a converging mirror is a convex, oh, I said mirror, lens is what I mean. It's a nice convex lens. It looks something like this. Now this here is the vertex of our lens. It's this little center point here. And now here's what we're going to do is we're going to label our 2 focal lengths on either side of this center point. So I'm going to say my center point is right there. We are today going to practice drawing a 2-scale diagram. So here's what my scale is going to be. I'm going to say for me that 1 centimeter on my paper, on my computer screen, is going to equal 10 centimeters in real life. That is a nice scale that works well for me. It's probably not a great scale that works well for you, or maybe it is a great scale that works well for you. I've actually found that 1 centimeter to 10 centimeters works pretty well on student papers, depending on what kind of numbers that you have. But for this particular problem, it works nicely. Now, here's what I'm going to draw. I'm going to draw my focal lengths. They're each going to be 10 centimeters away from the center, which is 1 centimeter on my paper. So here, right here, this is my center. I'm going to go 1 centimeter over to the side. And that right there is going to give me my first focal length. I'm going to go another centimeter over to the side using my ruler, and that's going to give me my second focal length. So I'm going to call this one F prime. I'll call this one F. Now it says the distance to the object is 20 centimeters. Well, hey, that is a nice positive length here. So we are going to draw that where we always draw objects. And it's 20 centimeters, so that's going to be 2 centimeters on my paper. Gotta get things lined up here. Okay, so that's gonna be 1 centimeter, 2 centimeters, and so I'm gonna draw my little object. Whoops, didn't mean to make a mark there. Let's go back, go back, go back, go back. Okay, let's see, 1 centimeter, 2 centimeters right here, and this is where I'm going to draw my little object here. Great. Now let's follow our 3 golden rules. The first golden rule, you know, is that a line that goes through C continues on going on its merry way. Now this is where you are using a ruler, but I cannot use a ruler. I can use a ruler for the other parts, but I can't use a ruler for this part. But you are going to use a ruler, and it's going to just come out so lovely. We're going to start on the top of our object. We're going to go down through C and continue on our merry way, unaltered by this lens. Next, the next rule, this is a converging lens. For a converging lens, the second rule looks something like this. Hello, I would like to change my color, please. The second rule looks something like this. It says a line, oh gosh, oh no. Has this happened? Oh no. Oh gosh, oh my. Okay, wait, this is good news. This is not as bad as I thought it was. I thought we were in deep doo-doo, like serious problems, but we're not. I thought I was going to have to restart my computer. Okay, here's what's going to happen. You're going to draw a line that is going to go through F prime first, like this. It's going to hit the center line here and refract, oh gosh, parallel to the optical axis. Again, this is where having a ruler would be so very helpful, but I do not have one. You have one though, and it makes your lines nice and straight and beautiful. Next, my third rule for a converging lens, I'm going to take a line that goes, let's do, color choices can be so difficult sometimes. Let's go red. I'm going to draw a line that's going to go nice and parallel to the optical axis. That line that goes parallel to the optical axis is then going to refract down through F. This is a converging lens. If it were a different type of lens, like a diverging lens, then it would refract through the other F. And here mine don't converge very nicely. If you are using a ruler, they do converge oh so nicely at that point, and you say, wow, that's so perfect. And I'm like, yes, it is so perfect. It looks so nice. Okay, wait. Yeah, no, still not quite there. But darn. Okay, well, close enough. We'll call it for me for today, but yours is nice and perfectly lined up. It just looks so stunning. And here's what your eye would see. Your eye would see this refracted light ray, this refracted light ray, this refracted light ray, and it would say, where did it come from? Oh, look, they all seem to converge right here. And that is where you would see the top of your image. Hey, go ahead and write down on your paper, what 3 adjectives would you use to describe this image? Did you say that it would be real? And again, my pen is so slow today. I might just say these words out loud instead of writing them down because, wow, this takes a long time to write. Did you say that this would be real because it's made of real light rays? Did you say that it would be inverted? I'm just going to write I-N for inverted, but you get the gist. You write out the whole word, inverted. And then finally, this thing, if you drew it right, if you had a ruler and if you followed all the rules correctly, then you should end up with something that is about the same size. I'm going to write SS because my thing is so laggy. Now here's what you can do. You're looking for DI and M, yeah? Why don't you go ahead and just measure with your little ruler, measure this little distance, your DI here, see what you get. Then measure this little length and this little length. They should be about the same, which means your magnification should be about what? Did you say 1? Because that would be totally correct. Okay, now that we've done this with a diagram, let's go ahead and do it with our math. I'm going to pull up a new, if it will load, I ideally am going to pull up a new drawing here, a nice new page. Although it might take about 5 gazillion years to load. Oh yes, here it is. And I'm going to write down once again all of my knowns and unknowns. I had that my distance to my object, actually maybe I won't because of how laggy it is today. Maybe I'll just trust that you have it written down. My distance to my object is positive 20.0 centimeters. Take your sweet and precious time. My focal length is, oh gosh, this is where you put the video on like 3 times speed. My focal length is positive 10.0 centimeters. And I'm going to start for part A. I'm going to look for DI. Hey, I got 2 equations, 2 possibilities for my equations. I could use 1 over the focal length equals 1 over DO plus 1 over DI, or I could use the magnification equation. Which one would you rather use? Yeah, same here. That first one, Miss Wilson. That is definitely the correct answer. Yes, totally. Let's write our original equation. 1 over F equals 1 over DO plus 1 over DI. Lovely. And now we are going to rearrange this equation to find for what we're looking for. I'm looking for DI, so I'm going to move this 1 over DO to the other side. Now you can do your algebra the way that I do my algebra, or if you say, Miss Wilson, I don't like how you do your algebra, no worries. You do it your own way. I just do it this way because it makes it very, very easy to type into the calculator with no confusion. I'm going to start by moving 1 over DI to the other side, and or moving 1 over DO to the other side to get 1 over DI by itself. I'm going to take all these fractions, I'm going to flip them and turn them into negatives. So I'm going to say that this is DI to the negative 1. Totally fair game to make that move. I'm going to say then that this is F to the negative 1 minus DO to the negative 1. All of that I'm going to take to the negative 1 on both sides, because when I do that, I get rid of that pesky little negative 1 there. I get a final statement, and yes, you should always write your final algebraic statement all nice and clean. Not with all these like negatives all over the place, but all nice and clean. My final algebraic statement is that DI equals F to the negative 1 minus DO to the negative 1. All of that to the negative 1. Now, after this, we are going to plug in numbers here. Please, whenever you plug in numbers, do plug in numbers with signs. I'm going to call this positive 10.0. You guys are like, I'm already done with this problem, and I have already typed it into my calculator. But thank you, Miss Wilson, for writing oh so very slowly. Yes, you are very welcome. Just trying to give you time here. You take your precious time. Okay, anyway, continuing on. I'm just plugging in numbers here. Hey, notice I always plug in numbers with my signs here. Plug that into my calculator. You've already done that in the amount of time it took me to write the first line of this equation. And when you did that, you got positive 20.0 centimeters for my distance to my image. Let's try part B. Part B asks for the magnification. You got 2 equations for magnification. You could either use magnification equals HI over HO, or you could use magnification equals negative DI over DO. Which one would you like to use? OMG, same. I'd love to use that one. That sounds like a great option. Let's use M equals negative in for my DI. Oh wait, actually I can't not write my original equation. I want to because this is so laggy, but I'm gonna do it because I have great resilience and persistence. Okay, here we go. Negative DI, my DI is positive 20.0 centimeters. That's right, ladies and gentlemen. Even with this level of lagginess, we still write our units. There's never a day when we don't write our units. All over positive 20.0 centimeters. Please don't you dare pull out a calculator. Just do this in your head. We got 20 divided by 20, and we get what, folks? You said negative 1. Check your sig figs. Negative 1, placeholder ordinary 1? No, you said negative 1.00. Yes, yes, that is a lovely, good-looking answer right there. Ooh, yes, lovely. Now, here's what we're going to do. When you finish a problem, you're going to end up with some numbers, and you're going to end up with a diagram. What you're always going to do every single time is check your numbers, check your signs, check that they match your diagram. Students who match their diagram to their numbers end up being really successful because they say, look, I got 2 sources that are telling the same story. Otherwise, if you've got 2 sources that are telling 2 different stories, then you can go back and you can fix it and you can make it better. So let's check it out. Do you like this negative sign here? The negative sign means that we should come up with an image that's inverted. Do you like that this is 1? That means that the magnification, those 2 things should be the exact same size. Do you like this positive 20 centimeters here? That means that our image should be real. And do you like this number, the 20 centimeters? Does it look like this thing is 20 centimeters away? 20 centimeters is the same distance as the distance of the object. Let's check it. Look at your diagram. I'll take a while to load to look at mine. But when I eventually look at mine, here's what I'm going to see. I'm going to see that, yeah, some things are starting to check out. I like that I got a negative number for my magnification because this thing does end up upside down. I like that I said 1 is my number of magnification because they end up the same size. And so that seems good to me. I also like that I got positive DI because my image does end up being real. And lastly, I like this number 20. When I'm looking at this length here versus this length here, I say, yeah, those are about the same. If this length is 2 centimeters, this length is also just about 2 centimeters. And so I feel really good about the kind of answer that I got here. Notice how I did the problem with a graph, with a picture. I did the problem with the math, and then I checked them against each other. That is a great recipe for success. Well, ladies and gentlemen, that's a little bit on lens equations. Today you learned 2 new equations. And when I say you learned 2 new equations, I mean you remembered 2 old equations. You also learned some sign conventions. And once again, when I say you learned, I mean you remembered them. And then we tried a practice problem where we tried a 2-scale diagram and we tried applying these equations. And you saw that everything just works out lovely. That is all for today. I hope you have a wonderful, wonderful rest of your day. I will certainly have a wonderful rest of mine. Bye, good people.